Is everyone ready? Let's get ready for chemistry!
At first glance, it looks like the nitrate ion has two single bonds and one double bond. So you would say that this is a double bond, and then these two are single bonds. In actuality, that's not really true. It's more like 1 1/3 of a bond. Since the double bond can be located in any of these three positions, this is more like having 1 1/3 of a bond in three places. So the double bond is split over three places. It's not a double bond in two single bonds. It's three 1 1/3 of a bonds. Hence the need for a discussion on bond order. So the bond order between the nitrogen and the oxygen is 1 1/3, or 4/3. The way to determine the bond order is to look at the number of bonds and the number of positions those bonds are, the number of equal positions those bonds are. So there's a nitrogen-oxygen bond, and all three nitrogen-oxygen bonds, all three of these bonds are all identical. That's what the resonance structures are showing us. So we count up the number of bonds, there's 4 bonds, and we divide that by the number of positions that bond can be located, here, here, or here. 4 bonds in 3 locations means this has a bond order of 1 1/3. If you look at methane, there are 4 equal carbon-hydrogen bonds here. They're all equal, they're all the same energy, they're all the same. So what's the bond order? At first glance, they look like single bonds. And in fact, they are single bonds, because bond order really only comes into play when we have to worry about double bonds located in more than one position. So each of these all have a bond order of 1. 1 for a single bond. At first glance, it looks like the bond order for the bond between the carbon and the oxygen and carbon dioxide. It looks like the bond order for that is 2. We would say there's 2 equal positions, and there's 4 bonds split over those 2 equal positions. So the bond order here is 2. And it's a double bond, so we would expect the bond order to be 2. You're forgetting that you can draw resonance structures for carbon dioxide, though. We can draw a double bond on both oxygens, or we can draw a triple bond on one oxygen and a single bond on the other, or we can draw the triple bond on the other oxygen and a single bond on the other. Let's look at the bond order for the carbon-oxygen bond in every case. Here you have 4 bonds divided over 2 positions. The bond order here is 2. Here you have 1, 2, 3, 4 bonds divided over 2 possible locations. The bond order here is 2. Here you have 1, 2, 3, 4 bonds divided over 2 possible locations. The bond order here is 2. So the bond order for carbon dioxide is 2. Let's look at the bond order for the nitrite molecule. You have a double bond that can be split between the 2 oxygens. So what you've got is not a double bond and a single bond, but 1 1/2 of a bond. How do you determine that that's what you've got? You look at the bond order. So we have 3 bonds divided by 2 possible locations. So the bond order here is 1 1/2. So each of these bonds is actually 1 1/2 of a bond, not a single bond or a double bond. Let's look at the bond order in formaldehyde. The carbon-hydrogen bond is a single bond. The carbon-oxygen bond is a double bond. If you didn't know what you were talking about, you might be tempted to say that the bond order here is 1 1/3 of a bond. But that's not true. The hydrogens cannot accept extra electrons, so the double bond cannot be located on the hydrogens. The only place for the double bond to be located is between the carbon and the oxygen. So we have 2 bonds divided by 1 position. The bond order here is 2, and then the bond order for these hydrogens is 1.
Is everyone ready? Let's get ready for chemistry! Ah! Yeah, 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 yeah.